Okay, this is Dr. Ryan Johnson, Calculus 3, Section 5.3 that I'm going to be recording beforehand because I'll be at University of Wisconsin-La Crosse to visit a former co-author. So let's talk about double integrals in polar coordinates. So you should have already done double integrals already, but now we go back to some of the stuff we did back in chapter 2 of switching to polar. So first let's start off with this. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this, love your neighbor as yourself. There's no commandment greater than these. Okay, let's dive right in. So here, remember how when we have double integrals, we can think of stuff, and then we can have a dA with like a region, or you could write it as the same stuff as like a dx dy. But in polar coordinates, our dA is going to be different. And so instead of adding up little boxes, we're going to add up little things that look like this thing. Okay? So this is kind of an exaggeration here. So imagine, imagine a region like this, and then you break it up into little guys, and little guy will look like this, where it's going to be, this is kind of getting close to dr there, and this change in theta is kind of getting close to a d theta. And so if you have this distance right here is basically r in theta. So my question, when I teach this lesson in class, I spend some time and just ask them, here's this region right here, what is its area? And, but since I'm making a video, I'm just going to cut to the chase and kind of give it to you. So if you think about this region as part of a circle, kind of part of, when you have a circle but minus the little circle, it's called an annulus. So it's kind of like, imagine you've got a piece of pizza, but somebody's taken some of the pizza away. Then how do we find out like the area of this piece of pizza? Well, what is the area? So what I would do with my students is I would say, what is the area of this big circle? So if the rate, this is r, and then this distance is dr, so then that makes this radius here would be r plus dr over 2. And this radius of the smaller circle would be r minus dr over 2. And so what is the area of the big circle? The area of the big circle would then be pi and then r squared, but our radius is r plus dr over 2. And the radius of the little circle would be, the area of the little circle would be pi times r squared, r minus dr over 2. Okay, so that's, so if I do this area minus this area, so minus pi times r minus dr over 2 squared. If I do that, I would get, try that again. I would get this, okay, the annulus. Now, what if I don't want the whole annulus, I just want a fraction of it? Well, then I can think, well, d theta is my angle there. And so if I was doing a pizza, then like say my pizza is split up into 8 pieces, then the angle of my piece of pizza is 360 degrees divided by 8, right? And so that's going to be 45 degrees. Whereas if I have an arbitrary angle, then the number of pieces of pizza I get would be 360, or actually if I'm doing radians. So if this was, if I had 8 pieces, then the angle, then d theta would be 360 over 8, right? And I guess if I'm doing radians, it would be 2 pi over 8. Okay? And so that means that if I think about how much of the area I have there, like what fraction of the circle do I have, I can then think about doing multiply both sides by 8, divide by d theta. Right? I've got 8 equals, but it's really, I don't want 8, I want 1/8. So like 1/8 is then like d theta over 2 pi, right? And that works for if I have 9 pieces, 10 pieces, whatever, I'm doing the angle divided by 2 pi gives me what fraction of the annulus I'm getting. So if I take all of this times d theta over 2 pi, then I get the area of this guy, because I'm taking its fraction of that annulus. So if I multiply this all out, let's move down to over here. So multiply it all out, so I've got d theta over 2 pi times pi times r plus dr over 2 squared minus pi times r minus dr over 2 squared. Well, I can cancel out the pi's. And so I've got a d theta over 2 times, let's FOIL that out. So you get r squared, and then an r times that added together would be, you'd get a, so plus r dr, and then plus dr squared over 4 minus r squared minus r dr plus dr squared over 4, kind of foiling both of those out. Simplifying, r squared minus an r squared. Dr squared over 4 is going to be minus a dr squared over 4. And so you're left with d theta over 2 times 2r dr. Well, the 2's cancel out, and we're left with r dr d theta. And so that's what our dA is. This is why, so if you got lost during all the algebra, the main takeaway is that this is why when we switch to polar, we get an extra r when we switch to polar. Because when you do Cartesian, in your little boxes, those areas are dx times dy because they're little rectangles. But now I don't have rectangles, I have pieces of annuli. And so my pieces of annuli have area r dr d theta. And so you get an extra r when you switch to polar. So let's do an example here. So let r be the region between here and here. Find this. So my region, that's all region stuff. That's all r. Okay, so that goes there. So then you got to also switch this thing to polar, and you got to convert this guy. Okay, so let's convert these equations to polar. Well, this is a pretty simple one. So r squared equals 1, so r equals 1, and r squared equals 5, so r equals square root of 5. That wasn't too bad. And so then I can do there's no theta mentioned. So when there's x's and y's and none of them are mentioned, they go from their full range, negative infinity to positive infinity. But when theta is not mentioned, it goes its full range, 0 to 2 pi. And then r goes between these two numbers, 1 and square root of 5. Okay, then we got to convert the function. Let me change colors for converting functions. Let's go red. So now I'm going to do the function. And so I'm going to convert x squared becomes r squared cosine squared theta, and a y becomes r sine theta. Okay, and then let's do another color for the dA, And so dA becomes r dr d theta. And so then we can simplify, multiply everything together. So you notice that one of the great things we did here is that setting up an equation with x's and y's with that equation is a huge pain, but it's just constants when polar. And that's why switching to polar is nice here. So then multiply this all together. So you get 0 to 2 pi and 1 to square root of 5 times r cubed cosine squared theta plus r sine theta dr d theta. I moved r squared. So I moved the pink r, in with the red r's. Okay. So now, how do I solve this integral? Well, I'm integrating first. Dr is on the inside, so I'm integrating with respect to r first. So that's going to be keep my 0 to 2 pi there. I like to use brackets for this sort of thing, so then I get a 1/4 r to the 4th cosine squared theta plus 1/3 r cubed sine theta, and it goes from 1 to square root of 5. Still have a d theta, and so that's going to be, let me move my integral over since this is going to start getting messier and messier. Okay, so then plugging in my square root of 5, I've got, square root of 5 to the 4th power is like 5 squared, so 25 over 4 times cosine squared theta plus square root of 5 cubed would be like 5 square roots of 5 over 3 sine theta minus plugging in 1/4 cosine squared theta, and then minus the 1 there, minus 1/3 sine theta d theta. Let's combine our like terms before we integrate with respect to theta. So 25 over 4 minus 1/4 is 24 over 4, otherwise known as 6. So 6 cosine squared theta, plus the other one is not as nice, 5 square roots of 5 over 3 minus 1. It's a bad 3. There we go. Times sine theta d theta. Now you might notice that this guy needs to be changed. So cosine squared becomes 1 plus cosine 2 theta all over 2. So 0 to 2 pi. I'll let my 6 absolve that 1/2, so it becomes a 3 times 1 plus cosine 2 theta plus 5 square roots of 5 over 3 minus 1 times sine theta d theta. So doing this guy, we get so here's a shortcut, by the way. Oh dear. So a shortcut to this is, let me write it out a different way. 0 to 2 pi of 3 plus 3 cosine 2 theta plus 5 square roots of 5 over 3 minus 1 times sine theta. And that's all d theta. So when you're integrating trig functions from 0 to 2 pi, if the trig function goes back to where it started, you're going to, so sine, think about sine. Sine goes like that, right? So that's 0 to 2 pi. So sine is just as positive as it is negative. So if you integrate from 0 to 2 pi, you get 0. And cosine, similarly, and cosine 2 theta especially. So cosine of 2 theta would be there, and so it's just as negative as it is positive. And so integrating, when you integrate this, it'll become 0. So integrating this term will be 0, and this term will be 0. If you don't trust me, just do it out by hand, and you'll see it is true. And so using that little shortcut, I'm going to get integral from 0 to 2 pi of 3 is 6 pi, and call it good. Okay, let's move on to the next one. Let's say I need to find the volume of z equals 16 square root of 16 minus x squared minus y squared over the region of x squared plus y squared less than or equal to 4. So it's always good when we're doing this sort of thing. This is my function. This is my region. The key word was over and of. Okay? So let's convert both of these to polar coordinates. My function converted to polar coordinates is the square root of 16 minus r squared. And my region is r squared less than or equal to 4, which would be r less than or equal to 2. And then you can kind of use it as a positive number, because when you think about like when r is greater than or equal to 2, you're going between 0 and 2 when you fill in a circle like that. Okay? So notice theta is free, so again, our integral for theta ends up being 0 to 2 pi. So anytime theta is free, it's 0 to 2 pi. There'll be some special cases of that, and we'll deal with that towards the end of this lesson. But most of the time, if theta is not mentioned, it's 0 to 2 pi. Whereas r is from 0 to 2, and then my function is square root of 16 minus r squared, and then I get an r dr d theta. On the homework and on some of the exam questions for this unit, actually there's no unit exam here, this will show up in the final. If you convert to polar and you forget the r, it becomes an impossible integral. But if you convert to polar and remember the r, it becomes simple u substitution. This is very common in the homework problems and on 1 or 2 problems on the final exam. So don't forget the r. Okay, so because we have that r, we can do substitution. U equals 16 minus r squared, which means du equals negative 2r dr. And so I can go from my theta is still 0 to 2 pi. My u, I think I might just kind of keep it as stuff to stuff, is going to be, so negative 1/2 u to the 1/2 power du d theta. So then integral from 0 to 2 pi, integrating that becomes a u to the 3/2 power, which means it's negative 1/2 times 2/3. And then like from stuff to stuff d theta. So then I'm going to move that fraction outside, but negative 1/2 times 2/3 becomes negative 1/3. Integral from 0 to 2 pi of, let's turn it back into r's. So then basically the r's become, so the u is 16 minus r squared, but now it's to the 3/2 power. From 0 to 2, because we switch back to r. D theta. But sometimes I like to do brackets. I know the book likes the straight line thing, but it helps me sometimes to think of it that way. All right, then we've got the negative 1/3, integral from 0 to 2 pi, of plugging in the 2, 16 minus 4 is 12, so 12 to the 3/2 power is, another way to write 12 to the 3/2 power is 12 times the square root of 12, minus plugging in 0 is, when r is 0, it's just 16. 16 to the 3/2 power is 16 square root of 16 is 4. 4 cubed is 64. Okay. D theta, there's no thetas mentioned, so I'm just like multiplying. And so I'm going to take the negative with the swapping of these guys and get, so 2 pi over 3 times 64 minus 12 squared root of 12. And call that good. Okay, moving on to the next one. This is one where you do need to be more careful. So, find the area enclosed by r equals 3 cosine 3 theta. Okay, now one should ask, what does that look like? Well, let's try to graph it as best we can. So when r, we kind of graph for different thetas. So when theta equals 0, cosine of 0 is 1. So this is at 3. Make some tick marks and change colors for what I'm graphing. Okay, let's graph in red. So it's at 3 there. Okay. When theta is pi over, let's do like pi over 12. When theta is pi over 12, then 3 theta is pi over 4. I don't know. Pi over 12 is really hard to do. What about like pi over 6? By the time you get to pi over 6, 3 times pi over 6 is pi over 2, and cosine of pi over 2 is 0. So what's going on there? That means there's an asymptote, and you think about how cosine works, it's going to be like going towards 0 there. Okay? Then, when theta is pi over 3, then I'm going to draw the pi over 3 line. When it gets from at pi over 3, cosine of 3 times pi over 3, so 3 times pi over 3 is just pi. Cosine of pi is negative 1. So then by the time it gets to pi over 3, it's 3 times negative 1 is negative 3. So it's out here. Okay? So when it would be in here, it's negative, which means I'm actually going to graph it here, like that. Okay? And then similarly, when we get to when pi is 1/2, theta equals pi over 2. When theta equals pi over 2, then 3 times pi over 2 is 3 pi over 2, and cosine is 0 then. So it goes back to 0 by then. And then if we draw kind of there and there, cutting that into thirds, you'll notice that it then does that, and then it's going to do that. And you can also graph it in Desmos, and you'll see that it does this. And when does it come back to where it started? By the time it gets to pi. When theta equals pi, then cosine, like that becomes cosine of 3 theta is cosine of 3 pi, which is the same as cosine of pi, which is negative 1. So when you're over here at theta equals pi, you're actually not here, you're negative, and so you go over there. So this is the problem when you have r functions that can go negative. So be very careful when r goes negative. Can be negative. Because in this case, we get back to where we started from 0 to pi. And if we go from pi to 2 pi, we just are going to retrace everything we did just with negative angles. So when I think about the area enclosed by this, I'm thinking about these guys. And you notice they're symmetric. And so it's going to be best to integrate over this leaf, which is from, so this leaf right here, which goes from like negative pi over 6 to positive pi over 6. Okay? That's going to work best because over this interval, negative pi over 6 to pi over 6, r is greater than 0, greater than equals 0 in that interval. And so that's going to make it your integral better. You don't want to end up with like negative stuff. Okay? So that means we're setting up this integral. So we're setting up an integral. So now our theta is not from 0 to 2 pi. It's from negative pi over 6 to pi over 6. and it's just 1/3, I'm going to multiply by 3 because and whatever it is here, multiply by 3 to get the other 2 as well. Okay, and then r goes from 0 to 3 cosine 3 theta. Okay, and then we're finding the area. So like, double integrals overkill for finding area, but that helps sometimes. It's like we're deciding this because it helps you with setting up integrals. And then dA, never forget the r, dr d theta. Okay? Well, that means that we get, we solve this to get 3 integral from negative pi over 6 to positive pi over 6 of integrating with respect to r is going to be 1/2 r squared, 0 to 3 cosine 3 theta d theta. So that's going to be 3 times integral from negative pi over 6 to pi over 6. Let's move the 1/2 out of there. Let's move that 1/2 outside the integral. And then we'll get r squared then becomes 9 cosine squared 3 theta d theta. So again, we've got a cosine squared. So then from here on out, it's kind of boring because you just use the cosine squared theta equals 1 plus cosine 2 theta all over 2, and you're good to go. So I'm going to stop here because I've run out of space anyway. All right, I'm going to pause here and start the next part in a second.